I think it's about the functional of electron nuclear kind of interaction.
Okay, yes.
And we have the electrostatic potential with density. So
Yes.
and then just I can see the increment for the potential. Less.
Well, maybe increment of density.
Yeah. It is.
Okay. Yeah. Thank you. Thank you. Everything was correct, and maybe we will try to add more. But let me ask Lola. Do you remember about 2 lectures ago we had a criminal with a fingerprint? Do you identify anything related to this criminal and fingerprint in this set of equations? Like which symbol in this equations relates to criminal or like to the face, and which one relates to the fingerprint?
I think the potential is related to the face.
Yes. Super.
Then the fingerprint, electron density.
Yes, absolutely perfect. Thank you. Thank you very much. Yes, absolutely correct. Okay. Okay. Lina, would you please share your opinion about the first typed equation here for energy electronuclear interaction? So why it does not have wave function? Like if one typically finds expectation value of some operator, often people use concept of wave functions. So how do you like what can you say why this functional form is used here?
As I remember, we use the functional derivative. We integrate over the potential times the density over the space to not to avoid using or to avoid our need for the wave function.
Yes.
This notation to just to relate to get the potential depending on our knowledge of the potential electrostatic potential and the density of electrons.
Yes, yes, very good, thank you. So if we would be just regular practitioners of quantum mechanics, instead of density, one would put here wave function and wave function conjugated, right? And instead we use density because we want in the DFT world to avoid wave function as much as possible. So, and I won't care to say something, but I do not know how to formulate a question. So
for next slide.
no, this one, this is important. Like, how would you interpret the last equation? How would you call it? What are its properties?
Let me see. Just a minute. So that that one is the external potential. So you take a derivative of the external potential and then.
No, wait. No. The lowercase v is external potential, and the uppercase v is energy of electron to nuclear attraction. So potential is defined in each point of space.
Oh, actually, I mixed with.
And V capital is just a number. It's like energy of all electrons to attracted to all nucleus. So it's just one number. Okay, please continue.
Professor, I already mixed up. The smaller one, the right side, that one is external potential, right?
Yes.
And in the left side, this external potential.
No, it's energy or total. Not total energy of electron to nuclear interaction. So it's not potential; it's energy.
In the right side, external potential, and the left side, that one is the upper one, right? That VNE equal to ZI divided by R. That one you wrote in the upper section. Yes.
So result of integration is typically a number, right?
Yeah.
And now if we know the result of this integration for different densities, right? So keep going, just sharing how you interpret it.
So we have the energy potential. Then actually you did the integration there. So after that we got the third equation and later on you divided all side with that I forgot the name of that.
Delta increment.
Okay, increment of density. Density. So using this one, we will able to find external potential for DFT calculation. I guess.
Perfect. Everything is great. Yeah, many thanks for the help. So let me summarize everything you've told. So by the last equation, you gave excellent context and explanation. I think with years, or maybe I can stop lecturing and just asking to speak one by one, and maybe it will be even better than standard style. So in the last equation, we have a procedure how to find external potential. And potential is typically used if we need orbitals. So here we are targeting practical way to set DFT procedure, and we will use orbitals. But orbitals are typically obtained in Schrödinger equation that has kinetic and potential energy. But how do we know potential? And here is this trick, how to get potential only based on the density. So if one knows the energy of electron to nuclear interaction and one knows potential in several values, like several distributions of density, and for each of them one knows energy. Then by making this ratio, one can find potential. Will you agree that this definition is similar to definition of derivative?
Dr. Killen?
Yes.
So before that, just checking. So this relation, the last line, it summarized what we explained last time, that the rho or the density of electrons lead to know the external potential, because if we know the density of electrons, then we get the energy. And using this relation, we can get the external potential, which leads finally to know the wave function and then the Hamiltonian.
Perfect. Perfect. Whew. You told it better than I ever could. Thank you. I'll probably cut your declaration from the whole lecture and make it as a separate, because I need to memorize how you formulate it. It's really great, and it makes connection to previous lectures. Thank you, Lynn. Yeah. So I don't know what to speak because you just covered everything. We have a procedure to get potential. And now the little question, would you agree that this last line is similar to definition of derivative in calculus, right? The only difference that in calculus one uses either straight dy over dx, or one uses partial dy over dx, right? And here is a new symbol. So instead of either straight or partial, it uses this Greek delta, which means to highlight some differences. So what are the differences?
So can I say?
Please, yes.
So as I remember the delta, when we use delta, we will have more than just one variable.
Yes. But
partial derivative, right?
It's so partial is used here. Partial is used for multi-variable calculus. But here we go further. Instead of like 1 or 2 or 3 dimensions, we have much more. So in regular derivatives, we just have increment from x to x plus delta x, just along one variable, x plus delta x. And here we are changing the three-dimensional function. So this delta rho means that as we blow the balloon, it was smaller, then we blow it a little bigger, it became bigger. So on the surface, it expanded, right? In three-dimensional expansion. And here we see how the energy, so to say, of a balloon changed if you pumped it a little bigger. So it is not one variable function, it's a functional. It's a three-dimensional distribution. So the stuff that we have in the last line is the extension of the concept of derivative to functional. So it's functional derivative because in the denominator we do have function. We have function. So. And this rectangular brackets symbolize that the energy is a functional of function of density. Whew. So it was concept number 1 out of 3. Yes.
Please can you go back to that slide?
Which slide?
The slide, the previous slide. Or did you delete? Okay, yes.
It is the same slide with just 2 dirty explanations. I think they are more destructive than helping. I need to erase this slide later.
I was trying to catch the last thing you said. Mm-hmm. You said that
after we are done with the lecture, I will share both slides and recordings. Sorry for not sending it before. I was just one-to-one meeting head to tail.
And Professor, don't remove that slide with note.
Okay. So you do not want me to clean it? Keep
no,
dirt.
You don't need to clean it. I like that one.
Oh, okay. Okay, thank you. I feel sorry for having this dirty slide because when I was evaluated by, like, as any faculty does, there was a criticism that this person doesn't know how to distribute material on board, and they look too dirty. Okay, so if we know potential, we can find energy. If we know the energy and the density, we can extract the external potential. So now I am going to explain a concept that I didn't announce, but it is important in the following sense. Why Dft is needed? If it is also uses concept of one electron orbitals, if it also gives same HOMO-LUMA energies, what is different, and why if it is not much quicker in computation, what's the benefit? So what's specific about Dft other than Walter Kohn and John Popple got Nobel Prize for it? There is a thing that is not available in Hartree-Fock, but it is available in Dft. So it gives some new information. And let me show. I was really pleased very recently. I noticed that not only class attendees look this recordings, but also there were a comment from, no, it's not here. It doesn't show here. Okay, never mind. There was a comment to previous lecture exactly asking this question, like not from the class attendee, but from someone in a different place. Like, why do we need Dft if it is so similar to Hartree-Fock? Your microphone is muted, but I see your enthusiasm.
Is that that's because of the exchange interaction part term?
Exchange is included in Dft, and Coulomb and exchange are both included. But in addition, based on the theorems that the Dft gives all forms of electron interaction, and there is another component of electron interaction which is neither Coulomb nor exchange. So when we were doing lectures in person, in face-to-face instead of online, I was offering class attendees to play a game at this point, at this slide. The game was that one brings one chair to the podium, asks two volunteers, and ask them to walk or run around the chair. And when the leader of the game claps, they should compete and sit on a chair, whoever first. Right? So you saw this game before, right? So it is a humoristic example of the correlation energy. So there are types of electron-electron interaction where mean field, where average distribution of all but one electron is not sufficient, because electrons repel each other. And if one electron is already sitting or moving on, for example, one side of an atom, second electron will not go there. But if it is moving, second one will move on the opposite side, right? So they dynamically correlate to position in space, dynamically, not only average distribution. And the energy
Yes.
of this, yes?
The question that person asked, he is absolutely right. So we need to understand the basic things like how to differentiate between the DFT and HF, means Hartree-Fock. Like for the electron density, it's I'm not able to understand that how to differentiate the electron density between the Hartree-Fock and the DFT. So,
So this correlation energy that corresponds to two electrons minus running around a chair is basically explanation how correlation works. So when someone is at one side of a chair, it is already occupied. You cannot go there. And if someone is trying to sit on a chair, it's like forbidden for others to sit there. So they know about position of each other, and it is not average position over time. It's like dynamically going forward. So when one is trying to describe it in more advanced form, and I know that you may complain to me to face or complain to each other that the course is challenging, but it is introductory, simplified course. There is a chance to make it more advanced with more theories, which I'm not going to do.
more advanced?
Huh?
More advanced from this course?
Right. So one can introduce multi-electron density. So we are using single electron density, and one can introduce multi-electron density. And then if the definition of the correlation energy is total energy computed from actual 2 electron density and product of 2 1 electron densities. So in the simplified, approximate way, they are similar, but there are differences between distribution in space of 2 electron densities, and it is the only time in the course we speak about it. So if one computes total energy of the 2 electron densities, and under x and y, I understand vector in space for first and second electron, and the product of 2 densities. So this difference will correspond to this electrons running around each other. There are quantitative numerical criteria, and there are some examples where this correlation energy becomes noticeable and defines outcome of experiment. Hartree-Fock theory does not include correlation. And if someone hates density function theory, likes Hartree-Fock, but still needs correlation energy, then there are ways to improve Hartree-Fock. So to improve Hartree-Fock, one adds the next level corrections. In Hartree-Fock, there are perturbation theory methods and second order corrections. It is called MP2, second order Molar placid perturbation theory. And next level of corrections are so-called configuration interaction, and the next level, which is coupled clusters. So those are quite expensive theories. They are much more expensive than Hardy-Fock and DFT, but they do provide correlation energy. And if one needs to compare with experiment, they are, you have maybe seen these abbreviations in drop-down menu of Gaussian. So there is a like molecular mechanics, semi-empirical, Hardy-Fock, DFT, and then these abbreviations, MP2, CI, CC. If you try to do some practical problem with it, it will take like 10 or 100 times longer than our regular calculations, but it will be more exact, more precise. Density functional theory is able, at least qualitatively, give this correlation energy, and it is one of the benefits of this theory. So here is a little silly example, just showing how the difference, how the single electron density and two electron density may differ. So it's only an example, it's not a mathematical proof. So for two electron densities, and we can put x as x and y, and I use only one dimension for first electron and one for another. It could be like localized in our area of distribution as cosine of x, cosine of y, and because they feel each other, there could be additional factor that depends on distance between electrons, and then such distribution will have a shape of, let's say, a sausage, or like elliptical, elongated along the axis. But if we will try to use product of two densities, so one dependence on x and another dependence on y, there will be no chance to implement such difference factor. They will be only product of one function times another one, and it will be homogeneously distributed along each direction. So it will miss dependence of one particle on another one. So it is just a little illustration which is very incomplete, but it shows that we just practically that two electron densities generally are more precise than one electron densities, and if one finds total energy out of multi-electron densities, there will be some corrections. Okay. Whew. Now we need to go to the second concept, and there will be not much symbols, but I'm getting scrambled with my own minds, and I close to failure in bringing this material. So I will correct errors on our next meeting if I do something wrong today. So the equations that I'm going to show will be not more complicated than the one that are already displayed here. So it is quite brief and simple. But there is a, I wouldn't say crazy, there is a very creative, non-trivial idea behind this equation. So if you were not following, and before, I invite you to focus right now. So it will be some, the idea is really cool. Maybe I'm not the best person to present it, but I'll try my best. So the theorems that we covered tell that density defines everything. a more specific density defines total energy. And total energy is basically the goal of, in narrow sense, it is a goal of any electronic structure theory. But theorems that from now on we should believe in, because we were trying to prove them and no one was objecting, do not tell how we convert density into energy. So it tells that knowledge of density gives knowledge of energy, but the path from density to energy is unknown, is not mentioned in the theorems. So it is a typical way how mathematicians are doing. They prove that solution exists, but they do not provide the solution, which seems a little unhelpful for people who do applied research. So now, based on this concept, suppose the total energy of electrons is composed, well, I even wouldn't say suppose, it is truly, total energy of all electrons is composed as summation of attraction to nucleus and repulsion of electrons to each other. And we'll treat kinetic energy later. So two types of Coulomb interaction with nucleus and with electrons to each other. And summation of these two terms with nucleus and with electrons should be constant. Should be total energy. Total energy computed out of density. So I didn't lie up to now. I just repeated consequences of the theorem. So now here is the trick. The theorem does not tell us at which proportions attraction to nucleus and repulsion with another electrons contribute to the total energy. In our realistic nature, this proportion is defined. But in the world of DFT, in the world of theorems, it is a degree of freedom. We can change proportion between attraction to nucleus and repulsion to electrons as much as we want, if we keep the total energy constant. So one can get a little bit larger attraction, a little bit smaller repulsion if they give the same total summation. We are allowed to do it. Make sense? Just please confirm. Yes or no? Or okay. Okay. Well, if you want me to repeat or explain different words, please let me know. So now next step. We are going to practice this change of the balance between nuclear and electronic energy. So electron repulsion energy is important, it is cool, but from practical point of view is our main enemy because it is very challenging. So suppose we select a parameter where value of parameter lambda equals 1 will correspond to real world. And then we will change this parameter lambda from 1 towards to 0. And it will be no, wait. Sorry, it is the place I'm always making errors. I may need to do my correction of errors and then update slides later. So real will be 0. Okay. Yes, I need to be consistent with myself. So if lambda equals 0, the factor here will be 1. If lambda equals 0, the nuclear to electron attraction will be the same as in the real world. Now we are going to change this parameter lambda from 0 towards 1. And as we increase lambda, the factor in front of electron-electron repulsion will become smaller. Smaller, 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 and then we will go to 0. Okay?
What function is that? Is that 1 minus lambda?
It is 1 minus lambda, Greek letter lambda. I apologize for my ugly calligraphy. So Greek lambda is an analog to Latin letter L, and maybe it was written this way historically. So, right? Greek. So we are moving lambda from 0 to 1. And in order to compensate smaller contribution from electron-electron interaction, we need to update value of the electron to nuclear interaction accordingly. Therefore, we put another index lambda at the bottom of this capital V and E symbol. So if lambda is set to 1, then there will be completely no electron-electron interaction, and the whole energy will be contributed only by attraction to nuclei. This sounds really crazy. It means our theorems allow us to tweak the world. So we design such world where electrons do not interact with each other. And therefore, it is, so this is a real world when lambda equals 0, and this is auxiliary world of Kohn and Schramm. So it's not real, it is fictitious, it is mathematical abstract concept. But if we accept this concept of the auxiliary world, we have substantial simplification. We can forget temporarily electron-electron interaction, do our calculations only with nuclear to electron attraction, which is much simpler, I assure you, and then return back to realistic world. So the plan is we are taking off from real, go to this auxiliary world, do calculations there, and then return back.
Dr. Killen?
Yes.
So is it like when we need to in some problems, if we need to solve the Schrödinger equation, for example, we can just use the ideal potential and then applying perturbation. So I can imagine that when lambda is 0, it's the ideal, and then similar to perturbation, close to the reality would be the auxiliary, right? Is it so?
Yes, I see that you are taking advanced quantum theory with perturbation methods. It's really great, and
it was long time ago, but
there is a connection.
Okay, I have another question, Doctor.
Just let me finish that, and then you continue.
Yeah, sure.
So, in traditional quantum theory, one takes ideal and then adds corrections, right? And here, due to the theorems, the correct result for the total energy will be immediately following from this, so to say, ideal, or I would better say auxiliary, from the calculations for lambda equals 1. So although it will be non-real auxiliary work, it will give, based on theorems, correct result for the total energy. And it is, so the Nobel Prize was given to developers of DFT for collection of these ideas, but this is another cornerstone idea which brings us from theorems to practical implementations of DFT. So sorry, Lynn, I interrupted you, but you had some comments and thoughts.
Me?
Yes.
Okay. So in previous slide, we said the total energy is composed of the kinetics and all the terms, electron interaction, neutron electron, nuclei, this, and these all things, column exchange and correlation. And then in this, and now we said we expect it just two energy, two kind of
yes.
energy.
So these three last things,
yeah,
Coulomb exchange and correlation, they all are labeled as electron. They all contribute to electron-electron repulsion. So the three things are combined into one. Then nuclear to electron attraction are here, and we just do not consider kinetic yet. So if you want to be mathematically precise, and your question is completely legitimate, I would say we are speaking about total energy minus kinetic energy of electrons. And
okay, now
this
it makes
is equal
sense.
to V sub NE plus V sub EE. Okay?
Yeah, thanks, Doctor. Yeah, no, it's true.
Okay, yeah, thank you for the question. Whew. So let's go forward. So we already covered this concept, and there are just better typed slides in better form, but it is the idea that we already discussed. Now, what did I promise at the beginning? The function derivative that we covered, auxiliary universe, and the third thing is how to compose density out of orbitals. And generally, why do we need orbitals? Why did we plot them in previous homework? Theorems of DFT do not require us to use orbitals, but just practically, it's very comfortable to use the concept of orbitals and concept of momentum operator acting on orbitals as a way to compute kinetic energy. So I'm not going to tell anything new. It is a standard part of like basics of quantum theory, but just in case, so that we to refresh, remind, and so that we all are on the same page, I'll bring it up. And I apologize if I'm repeating standard things that sound boring, but
Professor, can you go back to the previous slide? Yes. So where you wrote here lambda equal to 0, E total lambda equal to 0.
it is because I make errors. I think I need to be consistent. Let me go back to the one. So auxiliary word lambda equals 1.
Bigger way to
Yes. So 1 minus lambda equals 1. Yeah, I need to make sure that I'm consistent in notations when I will be sending slide. But let's believe what we discussed together. If I make this correction, does it make sense? Does your confuse disappear?
Professor, can you explain that equation? The E total lambda equal to 1. This one. Yes. The whole equation then equal to T rho R. Yes.
So T is kinetic energy.
Yeah. Yes.
V sub En, and here I should have the N to avoid confusion. Electron to nuclear attraction. So let me go back to the slide where we were doing the discussion. So if we increase lambda from 0 to 1, the electron repulsion becomes smaller and smaller, right? In order to compensate it, in order to have the total energy constant, we need to modify the electron nuclear attraction. And we modify it the bigger the parameter lambda. Therefore, instead of writing simply V sub Ne, we write V sub lambda comma Ne. So electron to nuclear attraction in the auxiliary world will be different than electron to nuclear attraction in the real world. And here is the slide you were asking about. So in the auxiliary world, which means total energy at lambda equals 1, it is contributed of total energy is contributed of kinetic energy plus electron to nuclear attraction, with understanding that here lambda is equal 1, and we do not have electron repulsion. Make sense? Yes? No? More explanation?
It's okay.
Okay. Yeah. Thank you. So let's go to things that are hopefully simpler. Let's focus on kinetic energy. So, Kay, would you like to tell about the first equation, the one that I'm enclosing in blue? Can you please explain what this equation means and how to interpret it?
Actually, I forgot. I can remember
Okay,
that
just
it's
a second. Just a second.
maybe lectures.
Then maybe this one. Can you explain this?
Rho is a momentum,
Oh, no,
right?
momentum.
No, it's a momentum. P.
Yes.
P is a momentum. So, I forgot. What should I say? No, I forgot.
So, like, what is kinetic energy?
Kinetic energy is
philosophically, like which car has larger kinetic energy? The one that drives 10 miles per hour or the one that drives 100 miles per hour?
The faster one.
Okay. So the bigger the velocity, the bigger kinetic energy.
Yes.
Right. So kinetic energy is measure of amount of motion.
Yeah.
Right.
Yes.
And and then if you are driving 100 miles per hour in the sedan, and someone is driving, and Sarah is driving Volvo truck that 40 tons with 100 miles per hour. Which one has larger kinetic energy?
Sorry?
Which car has larger kinetic energy? If you have two cars, one is very small, sedan or motorcycle, 100 miles per hour, and another is heavy loaded truck, also 100 miles per hour. Which one has bigger kinetic energy?
Both are same.
No. Which one? If
lighter.
Yes. Suppose another example. If there is a suppose it is no drivers. So we do it friendly to humans. So we just put empty motorcycle, run it, and smash into a wall. Motorcycle will break. Then we take a heavy truck, remove the driver, ramp it up to 100 miles per hour, and smash it into the wall. The wall will likely break because it has larger energy.
Yes.
Right? So heavier and quicker has larger energy.
So this one, this one obviously energy, and it's a kinetic energy because momentum. So you want to check kinetic energy of the electron using momentum and divided by the m is mass of the electron.
Yes, velocity. Yes. And what is the definition of momentum?
Theoretically. Just 1 minute. Just 1 minute. Momentum equal to rho equal to mv.
Let's give chance to someone else. Lola, what is momentum to your memory or impression?
I don't remember what momentum is.
So momentum is another measure of motion, and again, an object with larger velocity has bigger momentum, and object with larger mass has larger momentum. So the definition is mass times velocity, right? Now, if we take square of this, m squared v squared, in order to make it equal to mv squared, we need to divide it by mass just to make these two equations equal. Make sense? Right? Okay. Now, this, and I was not intentionally asking it to Sarah because she's practicing molecular dynamics and likely is operating these equations frequently. Now, if you go from molecular dynamics to quantum world, what is the definition of momentum for electron? What is the operator of momentum? If electron is a wave function that depends on maybe position and sometimes on time as well. Here we not necessarily need time, but what should we do with wave function in order to obtain momentum, in order to understand whether the electron hidden in this wave function moves quicker or slower? Just think for a second. Raise hand if you want to answer. Okay, Lina, please do.
Okay, so just take the derivative with respect to x or to the position. Then it times this constant minus I h bar.
Okay, exactly.
Derivative to the with respect to position.
Thank you, Wendy. So this yellow box is the simplest and maybe the main equation of quantum theory. So if you were taking it in the past, or you plan to take some courses related to quantum theory
this one, momentum for atoms or electron?
Momentum for electron. Momentum for electron. And most of things in quantum theory originate from this equation. So it's an important conceptual thing. So if you do not feel yet comfortable with this equation, let me give a little example. And sorry for doing it if you already know what follows, but suppose that with the typical simplest wave function of electron, especially in the world without atoms, when electrons are freely moving. So one of the typical wave function is so-called plane wave, imaginary exponential x times value of momentum. So here it is operator, and here is value of momentum. And if one applies this operator to this wave function, then one obtains extracting momentum from the wave function. So this derivative over space gives us momentum. And when we were practicing Hartree-Fock, it was already there. Maybe we didn't realize it, but it was in the equation when one finds molecular orbitals. Now we want, and maybe if you do not practice it every day, you do not feel very comfortable, but this is standard and comfortable operation that is typically done in calculations, and it is very useful to implement. So our goal is to use this concept of derivative over space to compute kinetic energy. And let me make one more box. Red. So if we plug this definition of momentum into this equation for kinetic energy, one will obtain this equation with second derivative. And second derivative over space. And this is exactly the form of kinetic energy operator in any quantum consideration. So if you write down Schrödinger equation, you typically see second derivative over space, which corresponds to kinetic energy. Okay, done with little visit to quantum theory basic. Whew. So I just explained what kinetic energy is. And we can speak that our electron-nuclear interaction in auxiliary world is a difference between total energy and kinetic energy. And then the external potential will be functional derivative of total energy minus kinetic energy in respect to potential in auxiliary world. In auxiliary world. So from total energy, we can get external potential if we know kinetic energy. And from now on, I will chase the kinetic energy. I'll check if time allows me. I know that I overuse your time. Let me just glance over a couple of slides and check whether we can fit things in short time or postpone for later. Whew. So in fictitious auxiliary world. Auxiliary world. The Hamiltonian includes only kinetic energy and external potential, which is electron to nuclear interaction. We can speak about multi-electronic wave functions in this auxiliary world. No one forbids us, especially if in the auxiliary world electrons do not interact to each other, and multi-electron wave functions will be just a product of single electron wave functions, so it will be not a big problem. Now, I'll probably try to quickly mumble the material, and then we'll start about from the same point next time. So for those who will be watching on the recordings, maybe if I quickly squeeze material in like 1 or 2 minutes. So if electrons do not interact with each other, if wave function is a product of one electronic wave functions, then it also agrees with an idea that factorization of wave functions agrees with chopping operator on terms, independent terms. So if there are many electrons, we can speak about momentum of first electron, momentum of second electron, and compose overall Hamiltonian with H capital as a summation of little Hamiltonians. Hamiltonian for first electron, Hamiltonian for second electron, Hamiltonian for third electron, and so forth. And then for each of the partial, this little h Hamiltonian, we can practice regular Schrödinger equation. This gradient, which is the same as second derivative, d2 r squared, plus external potential. And this Schrödinger equation for a single electron will generate us energies and one electron orbitals. Going a little bit forward, it is exact part charge orbitals that you were plotting in previous homework. Okay. And the next thing that I will probably will cover next time is how to construct total density of all electrons if we know all occupied orbitals. So it will be a derivation, how to convert Slater determinant of many one electron orbitals and multi-electron wave function to one electron density. It is not very complicated thing, but I'm already overusing your time, and I think it is enough for today. So out of my 3 goals, I completed first 2 and missed the last one. So how to get density out of orbitals. So meeting is done. Thank you very much for your enthusiasm and patience.